it's a great honor to get the Turing Award, and one of the things that it did for me was it caused me to reflect on what I had done and how I came up with the ideas that I was getting the award for. And that's what I'm going to be talking about today. I'm going to talk, first of all, about what was going on at the time that I invented the idea of data abstraction and how I came up with that idea. Then I'm going to talk a bit about what was in the CLUE language, which was what I developed in order to explore that idea. Then I'm going to talk a little bit about type hierarchy, and I'll conclude with a few remarks about what might happen next. Okay, so I got my PhD at Stanford, and I actually did my thesis in AI. I did a thesis on how to play chess endgames. And I realized partway through my graduate career that I really wanted to switch into systems. And when I finished my PhD, I went to work at the MITRE Corporation, and the first project that I worked on there was something called the Venus machine. And the Venus machine was a hardware architecture that was implemented on an Interdata 3. So what was going on at that time was that people were very interested in what they called microprogramming. And a microprocessor was sort of like a RISC machine. It had, this one I think had 16 instructions as best I can remember. It had maybe 16K of read-only memory. And the idea was that you would implement a richer instruction set using that read-only memory and that small set of instructions. Now, it might seem a little funny today that we weren't perfectly happy with that micro instruction set. And the reason that we weren't very happy with it, I think, was that, well, of course, the RISC sort of revolution hadn't happened yet, but also people were writing an awful lot of code in machine language then, and it's pretty tedious to write code in machine languages. Compilers were just not at the stage they are now, and higher-level languages were viewed with a certain amount of suspicion because people worried about whether the machine code they produced could be efficient enough and so on. So anyway, the project was to see what you could do with this microarchitecture, and I developed this Venus machine, which had a richer instruction set. And the most interesting thing about that machine was that it actually had semaphores in the hardware. I had read Dykstra's very famous THE system paper, and I was very interested in semaphores as a synchronization mechanism. So after I designed the Venus machine, of course, the next thing that happens is you say, well, is this good for anything? And of course, this is a standard programming language question. You know, you design your programming language, is it good for anything? And so to answer that question, I designed the Venus operating system. So this is a small multi-programming system, and this is around about 1969. Okay, so at the time Multics was being developed, it was early days. And so I developed the Venus operating system, and when I finished that work, probably around sometime late 1970, I then started to work on program methodology. So what was happening was that there was concern about the software crisis. Now, actually, we've never gotten rid of the software crisis, so this was more like the beginning of the software crisis as opposed to the ending of the software crisis. But people had started to become aware of the fact that we weren't very good at building software, and that our ambitions for what we wanted to accomplish greatly exceeded our ability to accomplish what we were trying to do. Another problem that used to happen at that time, and maybe it still happens for all I know, is that hardware was very expensive. Software, you couldn't really account for the cost. And therefore, there was a tendency to underbuy the hardware and expect the programmers to make up the difference. So not only we have these expensive, very small machines, but you were trying to do too much with them, and we didn't know how to build the software in the first place. So MITRE is a company that does mostly government contracts, and the government was very concerned about this software contract problem because how could they build the kinds of defense systems they were interested in under the circumstances? And so I started to work on this issue. Program methodology actually is interested, at least at the time, in two different and quite distinct questions. One of them was, how should programs be designed? What's a good design methodology? And the other one was, how should programs be structured? And the fact was that nobody had very good ideas, or at least the way software was being developed at that time, people weren't doing a very good job of either. What I'm going to do now is I'm going to tell you about some of the papers I read. Because I went back and read them for this lecture. I found it really interesting to do this. And I think that, I'm sure many of you have read these papers, but I suspect many of you have not. And I would recommend that you go back and read them I think computer science as a discipline isn't so great about remembering our history anyway, and it would be a good thing if we did that. Okay, and I'm not going to tell you about every paper I read, and I'm not going to try and say that the papers I'm leaving out weren't good ones. There were quite a few very interesting papers written at that time. So this is the first one I want to talk about. And you know, this is like revisiting our past, so it's quite interesting to do it, and it tells you a bit about the mindset. I should say, by the way, that when I gave this a first draft of this lecture to my students, I discovered how much they didn't know about the past, and it was quite interesting. So I'm going to try and tell you a bit about the past. Okay, so Dykstra wrote this paper in 1968 called The Go-To Statement Considered Harmful. And this was written as a letter to the communications of the ACM. One of the things you'll notice in these slides, by the way, is how many of the references were in the CACM, because at that time, the CACM was the premier journal, and the best papers went there. Then ACM made this unfortunate decision to turn it into a public, a rag. And now, as you know, about 3 years ago, they reversed course, and now they're trying to turn it into a serious journal again. So Dykstra wrote this paper, it's only a couple of pages long, in which he argued that go-to statements were not a good idea. And it may seem to you at this point in time that that is hardly an argument worth having. So why was this was in fact very controversial. And I didn't bother to go back and read the numerous papers that were written sort of against what Dykstra was saying. Instead, I want to summarize for you what he did say and talk a little bit about why people were opposed. What Dykstra said is kind of self-evident, thinking from today's perspective. He said, we have to reason about the correctness of programs. We do this by looking at the program text, but what we're reasoning about is the execution of the program, which is a dynamic thing. And so in order to try and simplify the reasoning process, it's a good idea if the execution of the program models what the text is doing in a pretty direct way. And if you use well-structured control structures, this is going to be true. If you use ifs and whiles and procedure calls. But if you use go-tos, this is not always true. And then he went on and talked about debugging, and he made the point that, suppose you're in the middle of debugging a program and you're at a particular point in the execution of the code, and you're trying to figure out what's going on here. Well, in order to answer that question, you sort of have to understand how you got there. And if you're using well-structured control structures, it's not that difficult to do, but if you're doing go-tos, you could have come from anywhere. And just as an aside here, I'd like to point out that in those days, people even wrote non-reentrant programs, and I had to maintain such a program where it actually modified its own code in order to get rid of one instruction so it could take a branch faster. So if you think go-tos are bad, that kind of code is even worse. Now, the reason that people were opposed to this, I think there were two reasons, maybe three. Okay, one was just plain old conservatism. We do it this way. A second one was probably concern about performance. But I think the third one, and maybe the most significant one, was that the programming languages at the time didn't have that great control structures. So people were using labels in various ways that are actually fairly legitimate in the absence of reasonable control structures. Like, for example, if you pass a label as an argument to a procedure, you can use that as a very nice kind of exception mechanism where the procedure jumps to that label if the exception rises. Or if in the absence of a case statement, you can use an array of labels as a substitute for a case statement. So I think there was also a lack of expressive power in the programming languages, and that was another thing that was worrying people. Okay, the next paper I want to talk about is this very famous paper by Nicholas Wirth, Program Development by Stepwise Refinement. And Wirth was interested in the question of how do you design. And this is a paper about top-down design. So, Wirth says, well, start with your program statement so you know what it is you're trying to implement, and then make a single decision which will give you a kind of an abstract program with a bunch of pieces that have to have the details filled in later, and then repeat the process. And the example he used in this paper was the 8 queens problem. And his first decision was, start with the first column and then extend to the second column, the third column, and so on. So that was a reasonable strategy. And, top-down program development, you have to do a lot of top-down when you design. Otherwise, how do you know you're ending up with a solution to the problem you're trying to solve? And this was just a very early paper that pointed it out. On the other hand, Wirth wasn't particularly interested in the program structure that resulted. So he sort of thought about the program as just being one great big program with more and more elaboration as you went down. Another thing Weert pointed out, which is certainly true, is that when you follow a top-down process, you are actually designing a family of programs. And each time you make a decision, you sort of focus in on one member of that family, but if you have to change that decision later, you can then go and look at another member of the family. Okay, now here's a very famous paper, also Dave Parnas's paper, Information Distribution Aspects of Design Methodology. David wrote two papers, this one and a later one about modularity, at about the same time. And David was more interested, I would say, in the structure of programs than in the design methodology. And he was very interested in modularity. So what he says in these papers is, you got to have modules in your program. I'm not exactly sure what modules are, but modules ought to have narrow interfaces. And furthermore, they better have very small connections. And then he has this famous statement in this paper, the connections between modules are the assumptions which the modules make about each other. And this is actually an important statement because what he's saying is it's more than what you might see on the surface. It's everything they use to communicate and every assumption they make about how the other one is behaving. You have to realize how early this is. You know, people didn't really know how to write specifications. In fact, they weren't even talking much about specifications. I don't know if you remember, but in those days, in some sense, languages didn't have specifications. Instead, the compiler was the definition of the language. So, you know, this is pretty early days for making this statement, and he was really on the track of let's try to really say what a module is doing. Okay, so I read these papers and a whole bunch of others, and I wrote a paper of my own. And this paper was, first of all, influenced by these other papers that I read, but it was also influenced by my work on the Venus system, where I realized that I had actually been using a design methodology without sort of thinking about it. And what that paper proposed was that it's very similar to Parnas's work. It said the entire system should be broken up into these things I call partitions. Each partition has inside it some hidden state, and it provides a set of operations, and the only way the partitions interact is by making calls on one another's operations. And it's not an accident, I think, that I came up with this idea after work in operating systems, because operating systems, at the very least, have a very strong... Okay, I'm going to need someone to open my water bottle. Truly. Yeah, thank you. Because this one, I think, has already been drunk out of. Yeah, thank you. I appreciate it. Because operating systems, at the very least, had a very strong notion of modularity between the operating system and the user code, even if they may not have been so well designed inside. Venus happened to have carried this idea fairly far, but without my actually thinking about a methodology in advance. Okay, so I wrote that paper, and it was published, as I showed you, in the fall of 1972. I wrote it sometime in 1971, and in September of 1972, I moved from MITRE to MIT. So I came to MIT, and what I was really interested in was how can these ideas be applied to building programs. So it seemed to me that I'd been reading these papers, and especially the papers of Parnas and my own ideas, and we sort of understood what to do when we'd give a particular example. But when you tried to take that idea and apply it to some other program you were working on, it was absolutely unclear how to proceed. So I was very concerned about how to make these ideas more usable in practice. And so in the fall of 1972, I was thinking and thinking and thinking about this at the same time that I was trying to get used to being a professor, and I was teaching a course in hardware without a background in hardware, and so there were a lot of other things going on. But at any rate, sometime in the fall of 1972, I somehow got this idea of connecting partitions to abstract data types. Now, in retrospect, you can kind of see, that it was sitting there. So I thought about this, where did this idea come from? I have absolutely no idea. Okay, I think that it came from where ideas come from. In other words, you're thinking hard about a problem. The idea, in some sense, is there, waiting to be discovered, and somehow by magic you put the two things together. And you're probably not the only person to do it, because there's a tendency for these ideas to sort of pop up at a particular time, and more than one person thinks of them at that time. Okay, so I thought about connecting partitions to data types. In the spring of 1973, there was this SIGPLAN, SIGOPS interface meeting in Savannah, And again, isn't it interesting? It was SIGPLAN and SIGOP, so there was a lot of stuff going on. It was mostly about languages for building operating systems in. But it turned out that the focus of the conference was primarily on programming methodology. And I gave a talk on my ideas on abstract data types. And Steve Zyliss was there, and he had written a little paper that had a similar idea in it. And so Steve and I started to work together. Now, Steve Zyliss was a graduate student at MIT, but he was an unusual graduate student because he was also an employee of IBM. And he was sort of going to school part-time, and he was much more mature and knew a lot more than your average graduate student. So Steve and I started to work together, and I remember this period of time, very fondly. In my memory, it never rained. Every day, Steve and I had lunch together. At that time where I worked at MIT in Tech Square, there was a big courtyard with trees and benches, and we used to go outside every day. We'd have lunch outside, and we'd be talking about our ideas. And by the end of that summer, so what I want to do is I want to tell you about what we were talking about. So Steve and I were working on this, and the first thing I want to point out is that between the two of us, we knew an awful lot about programming languages. So, of course, there weren't as many programming languages then, but there was Fortran and PL1, and then there was the whole ALGOL stream of languages, and then there was Lisp, and probably some others I can't think of right now. And between the two of us, we were pretty familiar with all these, COBOL, for example. In addition, of course, we did a lot of reading of the literature, and mostly what we were reading was programming language literature at this point. So you may not know, but there used to be something called Extensible Languages, okay? And here's a couple of early papers on extensible languages. What was going on was that there was a lot of concern in the programming language community that by designing these higher level languages, you were taking so much power away from your users that you had to provide a way to give it back. And extensible languages were an attempt in that direction. And this first paper by Steve Schumann and Pierre Duran was a survey paper that talked about the two different approaches that people were looking into. One of them was what they referred to as a syntactic approach, where they would give the programmer the power to actually change the syntax of the language. And so, the little example that everybody says, oh yeah, that makes sense, is if you wanted to use factorial all the time, you could use a little factorial symbol for that. In truth, this is a dreadful idea, because, and actually what I wanted to mention was that another thing that was different about the mindset, maybe not as different as we might like, but different about the mindset, was that people were very focused on making it easy to write programs. And whereas today I think we've shifted and we think maybe it's more important to read them, at least I certainly believe it's much more important to make programs easy to read than it is to make them easy to write, because you write a program once, you yourself have to read it over and over again. Other people have to read it. Eventually somebody else maintains it. So reading matters much more than writing. And if users have much chance to muck around with the syntax, you can imagine how it might make reading programs very difficult. The other kind of extension that Steve and Pierre talked about was what they referred to as semantic extension. And this was a sort of a small data type idea. So think about a data type as just having a definition, so you can say stack is array with so it's just a description of how things are laid out in storage. But they had a little bit more because, for example, in Bob Balzer's thesis in 1967, he proposed that every data type have 4 operations. So he's thinking about collection types. And the operations are insert in the collection, remove from the collection, modify an element of the collection, and lookup in the collection. And he furthermore proposed that you could use syntax for that. So if you said s : x, where s is a stack, this would mean push. So that part was pretty awful. But the idea that there were a few operations, well, that might have been interesting, except there was no encapsulation idea, so it was just a convenience. And of course, it's kind of a straitjacket. There's many different kinds of data, and they're not going to all be happy with just 4 operations. Okay, this is a paper on Simula 67, okay? And this book, by the way, this structured programming book, I recommend to you. This is what we refer to as the little black book. It has 3 very interesting papers in it. This is one of them. Another one is by Dykstra on top-down design, and a third one is by Tony Hoare on data structures. And so this is a paper on Simula 67, and Simula, of course, had a way of relating the definition of the data objects with the operations that would operate on the data objects, but this was not really the idea that Simula was developed for. It was developed for simulation. They were very interested in hierarchical construction, and there was no encapsulation. Okay, here's another very important paper. This is Jim Morris's paper, Protection in Programming Languages, and he had a subsequent paper that sort of elaborated these ideas. So Jim was very interested in modular program construction, and he was concerned about how do you reason about the correctness of programs. And he wanted to be able to do local reasoning. So he'd like to be able to take a module and reason about its correctness without having to worry about all the other code that used the module. And this paper was in some sense way ahead of its time because he really had lurking in there ideas of rep invariance and abstraction functions. And what he pointed out in this paper was that if you don't have the right kinds of control in your programming language, you aren't going to be able to do this local reasoning. And he was worried about two things. One of them was modifications of objects from code on the outside, because after all, if you could modify the objects, then how could you have anything to say about what they looked like or what they meant? And then the other thing was impersonation. If you could create something that purported to be a stack and it wasn't coming from this code, then it might not satisfy the constraints. And then he went on to talk about, well, how could we enforce it? And he proposed what he referred to as seal and unseal, which are sort of like encryption operations in a way. The module was able to seal up the object, and nobody else knew how to seal, so there was some key. And then later on, when an object came in, it would unseal, and if it wasn't something that it had produced, it would fail. So that was his idea. Okay, so Steve and I read all these papers. Oops, one more. Okay, so this is Bill Wolfe and Mary Shaw, and one thing that's interesting here is that they are the other group that developed at the same time as CLUE a language for data abstraction. So they wrote this paper on global variable considered harmful, and of course, the title is related to Dykstra's title, and they sort of reasoned by analogy with Dykstra's paper. And what they were talking about was, in some sense, the algol stream of programs, which had this idea, which seems sort of really naive now, that you would just write one big program. It would be a huge outer block, and then there'd be inner blocks and inner blocks and inner blocks. And if pieces needed to communicate, you just put the stuff they communicated with in an outer block, and they could deal with that. And what Bill and Mary pointed out was that they're really talking about Parnas's ideas. There's all these extra connections. If a module, in addition to its formal parameters, has other things it can use, global variables, then it's very hard to reason about it. You don't really understand what it's doing. Okay. All right, so Steve and I worked through that summer, and at the end of the summer we produced this paper, which we shipped off to a SIGPLAN conference on very high-level languages. So now it's the fall of 1973, and we've managed to produce this paper. I'm going to talk a little bit about what it's in it. First of all, it explicated the idea of abstract data types, pointing out that encapsulation was very key here. You couldn't have code on the outside getting to the insides of these modules, and also that the set of operations is whatever the definer of the type thinks they ought to be, as opposed to that idea in extensible languages of having a predefined set. And the operations are the only way that you can use the objects. It also proposed a sort of a sketch of a programming language. So it had a mechanism for implementing abstract data types. It wanted polymorphism. So it wanted to be able to find not just a set of integers, but a set of t. Okay? And it proposed that you use static type checking, although we weren't quite certain you could do it, and the reason was we weren't sure what this polymorphism was all about and how that would play out when you really tried to explore it. And so we said, well, you can always use the seal and unseal idea of Jim Morris. And then we said, well, it should have an exception mechanism, and I'll get to that later. Okay, so that's the fall of 1973, and at that point I made a decision, maybe I had made it a little earlier, that I was actually going to sort of push on with this. And so I spent the next several years taking those ideas in that paper and turning them into a real programming language, which turned out to be called CLUE because of the first three letters of cluster, which was the mechanism we used to implement abstract data types. And the people who participated in this most were three new PhD students who showed up in the fall of 1973, Russ Atkinson, Craig Shafford, and Alan Snyder. And Steve stopped being a major participant in the project because he was working on his thesis on specifications of abstract data types. And there was a larger group of people who came to our design meetings, including the entire data flow group of Jack Dennis. So there was an argument early on about, was this going to be a functional language, by which was meant at the time, did it have side effects? But ultimately, I didn't go along with that because I believe programs fundamentally have to do with modifying state. And functional languages has changed a bit since then, but that was what it used to be at the time. Okay, I don't have many pictures. I would have loved to have shown you some pictures of Russ and Craig and Alan or Steve as of that time. This is a picture of me and Jack Dennis in 1974. Okay, so why a programming language? I actually had a rationale. Okay, and the rationale consisted of the following. First of all, programmers write programs in programming languages, so programming languages constructs are a very good way to communicate to programmers if you're trying to get them to understand how to build programs. So that was a good reason for building a program, a language. The second question was, does this idea really work? You know, if you have a programming language and it's really got data abstractions in it, and now you start building things with it, if there's something wrong with the idea, you'll find it out pretty quickly, because you won't have the necessary expressive power. Or another way of turning it around is, you know, what expressive power do you have to put in the language in order to make it usable in practice? The third point was, programming language is a mathematical object. You have to actually define what goes in there, even if the compiler is the definition in some sense. And so this was a way of making sure that the definitions weren't sloppy, but instead were precise. And then finally, we were very concerned about performance of some of these mechanisms, and so that was always a major issue. Okay, so we're doing language design. And language design is very hard. Okay, language design, of course, is very akin to interface design. So even if you're not working in the programming language field, whenever you design interfaces, you should be thinking about these issues of expressive power, simplicity, performance, and ease of use. And we fail miserably in the interface area, as all you have to do is look at many of our interfaces and you can see it right away. At any rate, these are the major things you think about in a programming language, but we had some other goals. First of all, we had the goal of minimality, which meant we wanted to sort of put as little in the language as we could manage while still putting in enough to get the expressive power we needed. By uniformity, we meant that the data abstraction mechanism should not be weaker than the built-in types. This is really a polymorphism argument. And then by safety, we meant put mechanisms in the language that allow us to find errors at both compile time and, if not possible at compile time, then at runtime. Okay. And I came up pretty early on with some restrictions also. Whenever you do a big project like this, what you want to do is you want to throw out everything you think you don't have to work on in order to simplify the problem. And that's what I did with concurrency. Early on, I thought I was going to work on concurrency, but in fact, I threw it out pretty early, and that was a very good decision because that would have been a big distraction. The go-tos thing was just like a religion. Sort of I was on the Dykstra side. And there was no inheritance in the language. I wasn't thinking about inheritance at all. The Smalltalk development happened at about the same time as CLUE, and I wasn't even aware of it till around 1975. There were a bunch of assumptions or decisions that were made early on, maybe almost unconsciously. Okay, so the first one was that CLUE was going to be a heap-based language with garbage collection. Okay, now, remember I did my thesis in AI. I had done huge amounts of programming in Lisp, and so I was really quite influenced by Lisp. But this was a really smart decision because what's nice about a heap-based language, of course you want garbage collection, otherwise you got all those errors. But what's nice about a heap-based language when you're combining it with data abstraction is you don't have to worry about how big the objects are. So you can do separate compilation without even having the code that you're going to be using sitting next to you, and you know how much space to allocate on the stack. The work that went on in Bill and Mary's group at CMU was a stack-based language, and they had a much more difficult time defining their language because of that. There was no block structure. I mean, there was block structure within procedures and within clusters, but there was no global block structure. So this is another Lisp thing, if you think about it. Lisp is a language where you just keep defining procedure after procedure, and then you put them all together. However, it was a compiled language. And I was very interested in separate compilation, including the ability to compile a using module, even though the code it's using hadn't been fully implemented yet. And then the deviation from Lisp was the static type checking. And this actually was also based in some extent on my experience in using Lisp, because I used to get so annoyed at the errors that I would have to find through debugging that a simple type checker could have removed in the first place. Okay, so I'm going to tell you a little bit about CLUE. And not everything, just some of the more important mechanisms. So first of all, clusters were the way that we implemented abstract data types. And what this slide shows you is that a cluster had a header, and in that header, we listed the operations that the cluster provided to its users. Okay, so this idea of a type being a set of operations was very directly expressed in the cluster mechanism. At the bottom of the slide, I have how you use an abstract data type. And what's interesting on this slide is this $ notation. The $ notation itself is pretty crufty, and I probably wouldn't do the syntax exactly the same way as I did back then. But there's actually a point being made here, which is that the view of data abstraction in CLUE was very different from what's going on in object-oriented languages, because we thought about the operations as belonging to the type, as opposed to thinking of the operations as belonging to the objects. So I'm expressing very directly here that I'm calling the create operation of the int set type. Okay? Now, if you think about these two different approaches, you can see that each of them has strengths and weaknesses. So if you put the operations in the type, that enables you to do a very nice job of binary operations, because I've got this implementation of the type, I can take in two int sets and easily check them for various sorts of comparisons. On the other hand, it doesn't support hierarchy or inheritance, and it also doesn't allow you to have different implementations of the same type within some part of your program. Okay, now I'm just going to show you a little bit of the inside of the cluster. This line rep here, that's our instance variables. So that's how we defined the set of instance variables. We did this through a type definition. It often was a record with many subcomponents. And then the last thing I wanted to show you is just a little bit of one of the operations. And what's interesting in this slide is this use of the word CVT in the header of create. That's sort of some remnant of Jim Morris's seal and unseal. So the idea was that these objects came from this particular cluster, and when they went out, we sort of sealed them up through CVT. So we converted them from the rep type to the abstract type. And then, I don't show you this, but an operation that took one in as an argument, we'd also put in CVT, and this meant go from the abstract type to the rep type. But however, we did this entirely with compile time checking, so there was no runtime expense to this. Okay, we wanted polymorphism in CLUE. It took us a while to figure out how to do it. So here I have a set rather than an int set, and it's got a type parameter. And down at the bottom, I show you the use of a set. We call that instantiation. So I'm saying, well, right now I want a set of integers. Okay, now the problem is that not every type makes sense to be an element of a set. Okay, now you might have been a little bit, perverted by what's going on in some of the object-oriented languages where they, say a priori object has equals and everybody has equals, but CLUE didn't have that notion, and equals is just an example. The point is that sometimes a parameterized type depends on certain properties of the parameter type in order for it to do its job. And in the case of set, fundamentally, you have to have some way of comparing the elements for equality. You need an equality relation, because if you put the same element in the set twice and then you take it out, you expect it to be gone. Okay? So it took us a long time to figure out a solution to that, but the solution we came up with was this where clause, where we simply listed the operations that the parameter type was required to have, and we gave their signatures. And then finally, you could use these. So that where clause sat there between the users and the implementers. Whenever you instantiated the type, we checked to make sure that the type parameter satisfied the where clause. And inside the implementation of the type, you were able to use these operations that were required. And the use is actually in this bottom line on the slide with the use of the equal symbol. So we had a moderate, what we referred to as syntactic sugar, where you could have a simple syntactic form, and we had a straightforward translation into the $ notation. Okay, so that's parameterized types. Now let me tell you a little bit about exception handling. This is another place where the world has changed. Okay, so in those days, exception handling was a very confusing topic, And John Goodenough wrote this interesting paper in 1975 in which he not only sort of laid out what the situation was at the time, but proposed some solutions. And what he pointed out was that, first of all, people used two different models for exception handling, the termination model and the resumption model. The termination model is the one we're all familiar with. The resumption model was that a procedure throws an exception, it's handled somewhere else, and when the handling is done, control reverts back to the procedure, which then continues on its way. And in fact, in PL1, which had a resumption model, you could even have it go either way. So, you could have a resumption model, but then the handler could sort of prevent the procedure from continuing. The other thing that wasn't sort of well laid out at the time was the question of how do you specify handlers. So today we're familiar with this happening at the call site, but in those days that was only one of several options. For example, you might in a block of code say at the top, I want this to be the handler for all uses of this other procedure, something like that. Okay, so with this in the background, we designed the clue mechanism, and I should say that we thought exception handling was very important. And one reason was that, first of all, you would like, if possible, to have preconditions that are simply true, because anything other than that means that you have extra connections between the module and its caller. But of course, even if you didn't do that, it's often the case that certain elements of the domain of arguments can't be handled the way as certain other elements. And so you need a good way of bringing this to the attention of the caller, and mushing it into some return result isn't a very good way of handling that. So of course choose is a very nice example of this because you can't return an element of the set if the set is empty. And what I'm showing you here is how it worked in clue. In the header of a procedure we would list the exceptions that could be raised, and then inside the body we could signal them. Okay, and then on the call side, so we went with the call, so we're talking termination, call site. All right, and then when we called choose, we could handle that exception. All right, so this is very familiar to you now because it's sort of the way we do things now, but there was one thing that went on in clue that I really think is better than what happens now, and that's what I'm going to talk about on this slide. It has to do with what do you do in the procedure that receives the exception. So really there's three things you can do. First of all, you might handle the exception. So I'm going through some sort of repetitive operation, I get the exception, that means I'm finished with that part of the program, I go on to the next. Okay, another thing you might do is you might propagate, and what that means is the exception has a different meaning to your caller, and so you sort of throw it up as a different exception which is meaningful at the level of your specification. But there's a third thing, and this unfortunately is always present, even though it may very rarely happen. And that is that the exception is not supposed to happen. So I just checked that the set was not empty, then I called choose, and it threw the empty exception. And the question is, what should a programming language do about this? So one thing a programming language can do about this is to insist that you write the exception handling code anyway. But that's not really great because that means your entire program gets full of this useless exception handling code. Another thing a programming language might do is to propagate that sort of blindly. And the problem with that is that then you never know what the interface of a procedure is because it's not what you listed, it's all this other stuff as well. So the clue solution was to turn this exception, any unhandled exception was turned into a special exception called failure. Failure was always another possibility for any procedure that you called. And clue exceptions actually had arguments, and the argument of the failure exception was a description of the exception that had caused the failure to happen. And I think that this is, in fact, a very good way of dealing with exceptions in a programming language. Okay, the final thing I want to tell you about is iterators. So we were very worried when we were doing the design of clue about what to do with this kind of structure, which is, in fact, something you really want to do. What's the point of having a collection object? You gather together all the elements, and then you want to do something with them. And typically that takes the form of a for loop. Okay, so in the, and given the mechanisms I've described for you so far, there are only two solutions that we could see. One of them was you could destroy the collection. So I might have a select operation for sets that removes elements, and this way I could go through the set and iterate over it, except that I maybe didn't want to destroy the set because I might have wanted to do something with it later. The other thing you could do is you could complicate the abstraction, so I could turn it into an ordered set. This would give me a way of iterating through it, but it's not a good idea to complicate abstractions. You'd rather stick with the simplest abstraction you can think of. So in the summer of, I believe this was 1975, I took my group to CMU to visit Bill Wolfe and Mary Shaw, and this was the 3 students I showed you. And they described to us some work they were doing on what they referred to as generators. And generators are a little bit like the way that Java handles iterators. You know, they had a few operations. They were tied to a for statement, and various things that were going on in the for statement related to particular calls of operations on this generator. And we could see that this was going to be a way of us solving the problem with that we were looking at, except that we thought it was an ugly solution. And so on the plane flying home from Carnegie, Russ Atkinson invented iterators. And iterators are, they're like procedures. You call them, but instead of returning, they yield. And when they're finally finished producing everything they're going to produce, then they return. And you could call an iterator in a for loop. So here I am calling the members iterator of the set abstract data type. And that's going to yield one member after another until it's produced all of them. When you enter the for statement, we call the iterator. Each time it yields, we run the body. And then at the end of the body, we go back into the iterator to ask it to yield the next statement. And when it's finished, that's the end of the for loop. So that was how it worked. Here's the iterator. This is an implementation of the members iterator using, in fact, a call on the array iterator. Okay, and you can see in there the header, which says it's going to yield an element of type T. And you can see the yield statement where it produced it. Now, of course, we were very worried about how to implement iterators, and it turned out that we had a very nice, simple, efficient, and elegant implementation. Namely, we took the loop body, we made it into a little procedure, we passed it to the iterator as an argument. And this allows recursive iterators, nested iterators. What it doesn't allow you is to have 2 iterators sitting side by side. So I can't go over 2 lists simultaneously. I can't write what's fundamentally a coroutine. This is a limited form of coroutine. And we did this explicitly. We limited the power of iterators. The ones that Bill and Mary were looking at were much more general, so that we could get this very straightforward, efficient implementation. Okay, so that's it for Clue. The thing you can see about Clue is it was way ahead of its time, because what work I'm talking about was all done in the 70s. We pretty much had finished the design by about 1978. At that point, I went on into distributed computing. I designed a language called Argus, which is an object-oriented language that allows you to write distributed applications. It had transactions in it. It had a whole bunch of stuff in it. And the truth is that I mostly moved out of the programming language area into the systems area. And most of my research from 1970 on has been on distributed systems. And I've done work in replication techniques, and right now I'm working on information flow control, and so on. But I didn't ever stop completely doing programming languages, and I should say that my work on programming languages has been very influential in all the work I've done since then, because it's always sort of forced me to think in terms of what's the interface, is this a nice simple thing, how do you trade off the expressive power versus the ease of use, and so on. And this is very useful in the systems domain as well as in the programming language domain. What I'm going to tell you about in the rest of the talk, and it's not going to be much longer, is a little work I did. I did continue my interest in programming methodology. I looked a lot at how do you specify data abstractions, how do you prove correctness of data abstractions. I developed a course at MIT where I taught the students how to do modular program construction, and so on. And I also did a little work on type hierarchy, which after all was something that wasn't in Clue and it wasn't in Argus. Okay, what happened was I was invited to give a keynote at Uppsala. And this was in 1987, and I thought, well, this is maybe a good chance for me to look into all those object-oriented languages and see what's going on with them. And what I discovered was confusion. And the reason I found confusion was because there was this inheritance mechanism, and it was being used for 2 different purposes, and people hadn't quite sort of gotten through thinking about this, and they didn't realize that these purposes really weren't the same, and that they, in fact, sometimes were contradictory with one another. So I thought about this, and I wrote a paper. I gave this talk at Uppsala, and then I wrote a paper. And this is basically what I said in this talk. First of all, I pointed out that implementation inheritance violates encapsulation. So Smalltalk had encapsulation. Users of one of these classes weren't able to get inside and look at the private stuff. But the subclasses could do whatever they wanted. And this meant that if I had this nice class, and I then decided I wanted to re-implement it, well, I was sort of in a pickle because I had all those subclasses that I had to worry about. And to be blunt, I personally don't think inheritance is very interesting. I mean, I implemented stuff that was very similar to this include just by using the object as part of the representation and calling its operations, and I just don't think that this is such a big deal. On the other hand, type hierarchy I think is quite interesting, and it really was not well understood at the time, and I read papers that were very confused about it. So I remember a paper that claimed that stacks and queues were subtypes of one another, and the reason was they, invented these sort of neutral operation names, add and remove. So they both had operations add and remove, and therefore, voila, okay. And clearly, and that was sort of as far as the thinking had gone, is maybe, we needed to talk about the operations, and they had names and signatures, and that was the end of the story. And clearly that's not a true statement, because if I wrote a program expecting a stack and I got a queue, I'd be really confused, because I would expect FIFO versus LIFO. Okay. So in this paper, I came up with this little statement. Objects of subtypes should behave like those of supertypes if used via supertype methods. Sort of common sense. And this was the keynote I gave at UPSLA in 1987. I wrote it up as a paper. What happened was it got picked up. And I discovered 5 or 10 years later that there was a community on the internet, and they were all discussing what they referred to as the Lascaux substitution principle. And this is still going on. They refer to it as LSP. And that was just sort of amazing. But, if you look at it, it's intuitively right. And I did work later with Jeanette Wing where we tried to formalize exactly what it meant. Okay, I said one more thing in that paper. I said subtypes are useful for polymorphism. What I have on this slide on the top line is the way CLUE does it with the where clause. And then I have some, hypothetical notation here where you replace the listing of the operations with the subtype. I actually think that's a better mechanism. But it's interesting to realize that in either case you need proofs. Okay, in the CLUE thing, you would really have to prove every time you instantiate that, say, the equal operator really is an equality relation. And in the subtype arena, you really have to prove that a subtype behaves, it satisfies the Liskov substitution principle. So it's not enough to have the syntax, you've got to have the semantics along with it. Okay, so that's basically the end. So what I discovered when I was doing this sort of looking back was that the world had changed. And I realized this primarily by talking to my students who just hadn't a clue, no pun intended, of what things used to be like. They didn't know about block-structured programs. They didn't know about algo-like languages. And in fact, I remember at the time I got the Turing Award, there was a quote by somebody on the internet saying, "What does she get that prize for? Everybody knows this." So the world... So the world has changed, and actually, I mean, that's amazing, and it's wonderful. On the other hand, life is not so great, okay? The software crisis is still with us. This particular truth is more honored in the breach than it is maybe in the, there are a lot of very nicely well-written programs out there, but there's huge messes. I had the unfortunate experience of having to sort of learn something about a web service program recently, and I discovered that the thing was full of global variables, and not only that, but they had passwords sitting up there, and I guess they were just hoping that nobody by accident accessed it and so forth. So yeah, we sort of know how to do things right. We have a real education problem, I think, and this has been true ever since programming came along. Joe Blow can program. And a lot of people think they don't have to know what they're doing. Anyway, so things are not so great, and the software crisis is still with us, even if we're professional about it and we know what we're doing. So it seems to me there's a lot of work left to do, and you in the programming language community, I know, are working on this. I've been waiting for 30 years for new abstraction mechanisms. We have abstract data types, we got iterators, but where's the next step up? I've been waiting for it to come. It would be very nice because if we could have a higher level of discourse, we could say things more, we could say more in an understandable way, and that would really help us write programs. These are two sort of obvious looming problems that appeal to me from my sort of systems perspective. The first one is we're being told that massively parallel computers are coming. I don't entirely believe this story because I don't believe that Moore's law is sort of a God-given thing where if it runs out, then therefore, voila, we have to have thousands of processors in our machines. Nevertheless, from a research perspective, it's an interesting question. There's no doubt that supercomputers are useful, and where you have a program that you can solve in a data parallel manner, you can actually take advantage of them. But if you think about these as general purpose machines, and I'm not talking about 4 processors or 8 processors, I'm not talking about your graphics processor and so forth, but I'm saying, supposing I have a database system, can I effectively implement it on 1,000 processors? And if we're in fact going to make any progress in that area, we need to have new paradigms for building parallel programs because this has been just a long, sad story. And maybe the map-reduce paradigm will be something useful. Maybe transactional memory. I mean, actually, that's just transactions again. Maybe that'll be useful, but I think there's a very interesting question there. How do we program those things? And then the other thing I'm very interested in is the internet as a computer. And here again, you see it coming. They're offering us cloud computing. The storage semantics isn't well worked out. The implementation, the runtime semantics is not well worked out. How do you write programs for those computers? And in fact, there's a funny disconnect in how we write distributed programs. You write your individual modules, but then when you want to connect them together, you're out of the programming language and sort of into this other world. Maybe we need languages that are a little bit more complete now so that we can write the whole thing in the language. So anyway, I just leave this as, a lot of open research left to do, and thank you very much.
Hi, Barbara. Dave Unger, IBM Research.
Yeah.
So there's an interesting complication to the Liskov substitution principle I wrestle with, and that is, if a type provides a set of invariants, any client may only need a subset of those invariants. Mm-hmm. So there's a huge number, there's power sets are big. Mm-hmm. So a subtype may be substitutable for some clients, but not for others. Mm-hmm. And the standard way we do that doesn't really capture that problem.
Okay.
What are your thoughts about that?
Well, I haven't thought about it at all, so all I'm going to give you is a sort of a first thought, and that is, I think what you wandered into here is a specification issue. So you could imagine that if you had, so I'm not sure this is if we get the specification right, the programming language can follow. So if you think about a type as having a lot of invariants, and if you think about that as being written in a specification, then you can imagine that a subtype, you could have sort of invariant-specific subtypes, and then you could start to think about how you put your programs together from there. So that's sort of the way I would start thinking about that problem.
Yeah, it seems to challenge the whole notion of subtypes because they're relative then to the
That's
context.
right. So it would be sort of a relative subtype, and you wouldn't treat it as a full-fledged subtype, but as a specialized subtype.
Yeah. Thank you.
You're welcome.
Hi, Henry Berger from Industry.
Hi.
I'm curious about the exception handling. I mean, the exception handling that in Clue is one that's well used now and seems to work very well. But as you say, as programs get more parallel, and you were doing work in distributed and parallel systems where a failure of one little piece doesn't necessarily need to cause the whole program to blow up. And so I was wondering whether you had any observations about handling exceptions when you have a lot more things going on at the same time.
So Argus had exceptions, and it was a parallel language. And what I recollect from that was that what's going on with that failure exception is you sort of are backing up. And the idea is that you're taking care of it at a higher level, probably by reverting to a checkpoint and throwing out a bunch of stuff. And I believe the idea in Argus was that this would propagate up through the process in which the exception arose. And if it wasn't handled by the end, then the larger unit, which was what we called a guardian, fundamentally an object, then you would have to fail that guardian. But if you could handle it at the highest level of that process, then it didn't have to fail the guardian. You just sort of got rid of that process or fixed up that process. I don't know that that's an answer in general, though, because we'd have to probably talk about a lot more examples.
Okay, but the Guardian, though, I take it is there's just one Guardian running on one processor.
Oh,
that's
yeah, one Guardian running on one machine. Right. Oh, absolutely.
handling a bunch of other
So a
and
Guardian
processes.
would be like, say, a file system interface on one of your servers. It would, support all access to files. And if something went wrong with that, well, that's fine because, maybe you had replication, so you put it together. So yeah, it's sort of piece by piece, process, Guardian, and Guardians were restartable, which is often the way you solve these problems. You fail the Guardian, bring it back up in a clean state, and then you can go forward again.
Okay, thank you.
You're welcome.
And I think that the Turing Award was well deserved.
Oh, thank you very much.
Hi, Barbara. Great talk. Thank you.
Thank you.
You for getting the Turing Award. And the work that led up to it, of course. The part that I was really interested in your talk was the story of how iterators were invented and the field trip to CMU. But I wonder if the iterator construct in Smalltalk, I don't know the history of that exactly and how that fit in and whether you were even aware of it in the early versions of Smalltalk.
I definitely was not aware of it. Iterators were not something that I went out and started looking in the literature for. I think there were iterator-like things in early Lisp dialects, but I was sort of unaware of them. And so, it was sort of a new invention, but maybe it was a reinvention. Yeah.
Thank you.
Yeah.
Phil Wadler, University of Edinburgh. I enjoyed that very much. I particularly enjoyed the history lesson. I agree with you completely that we all need to look at our history, that you learn all sorts of important things that way that you wouldn't know otherwise. So I want to add to your list one other paper. I'm sorry to say I can't remember the title or the year precisely. Shame on me. But it's John Reynolds' work on the polymorphic lambda calculus,
Yes.
which would have been close to that time, I believe, 73 or so.
Yeah.
And he showed that in a language with just 5 constructs, that you could completely simulate everything that you want about both data abstraction and polymorphism with the same set of constructs. And of course, it was wonderful because it's one of these times when you really know we're discovering stuff rather than inventing stuff, because a few years earlier, Jean-Yves Girard had done the same thing. So I want to add that paper to the list.
Okay.
I also want to ask you about your take on that, because that was going on at a very similar time.
So I am not a very theoretical person. So I tended to not pay an awful lot of attention to the more theoretical stuff. And so it didn't have much impact on me at all. I was always much more focused on what's usable, how do you write programs, how do sort of normal programmers write programs. So, sorry. Yeah. I was aware of the work, and I knew John Reynolds, but I didn't, pay an awful lot of attention to it. Yeah.
So, yes, I think actually we're all sorry. And one of the reasons that we're sorry is that you mentioned you based stuff on the ceiling idea of Morris, which is a brilliant idea. My current work, we're still exploring that.
Okay.
But of course, and then in Haskell, when we designed data abstraction in Haskell, we did it based on ceiling. But Reynolds had already shown earlier, you don't need to carry these seals around at runtime. You can do it all at compile time. And we all started to, oh, well, you could kind of erase it at compile time. You don't know. So actually, the relationship between what Reynolds did just with polymorphic calculus and then what Morris did and that you built on using ceiling is a very interesting relationship, right? Of course, we don't want to carry this stuff around at runtime. And the basic questions there, just the question of can you translate one to the other, has only been looked at fairly recently, say by Pearce and Sumi. It's still an open question.
Interesting.
Whether these can simulate each other. And yet, of course, it's much more efficient not to be using the clustering, the ceiling, the CVT. Haskell already suffers from the fact that we use something equivalent to CVT, and probably we shouldn't. So all of us, I think, still have very interesting things to learn from the theory as well.
Okay, great.
Hi, Arturo Sanchez, University of North Florida. Thank you for sharing your lecture with us. I have a couple of questions. They're really short. The first one, I want to hear from you your summary on the fundamental conceptual breakthroughs that, in your opinion, have happened today in our discipline. And the second is going to be a technical one.
Okay, so what I said was I moved, and I really have not been paying much attention to programming languages. I have been deeply embedded in the systems community, where, as I said, I've been working on replication techniques, and so I may very well, as a result of what I've done, go back and start looking at stuff. But if so, it will represent a change in direction from what I've been doing for the last 20 years.
The second question is related to a problem that I worked with a former professor of mine from RPI, and it's related to iterators. Do you think about the problem of while you're iterating on a set, what happens if the set is being modified?
Yeah. Yeah, and that's actually something that I talk about. I think I probably talk about it in the book that I wrote based on my course. And the way I proposed to handle it was to put it into the specification. So it's like an extra requires clause. Some iterators require that the loop body not modify the object being iterator. Others don't care. And so that was the way I proposed to handle that. It's definitely a problem. You have to capture that kind of constraint.
Thank you.
Yeah.
Hello, Peter Froelich, Johns Hopkins. I was going to ask you about the whole inheritance part, because you said Smalltalk hadn't been around yet, so no inheritance in Clue. And, but you also cited the Similar 67 paper, which had this, in my opinion, hard to understand block concatenation stuff in it. Did you consciously decide not to follow up on that and leave it out, or was it like my situation was before I read it like 6 times? You didn't get it, because I mean, a lot of people don't get the concatenation stuff at all. So is it conscious or accidental?
That's a hard question to answer. I was really interested in that idea of encapsulation. And so I didn't pay that much attention to Smalltalk because they didn't have encapsulation. And I also was, maybe it was another one of these limiting things where I really wanted to focus on what it meant to do data abstraction. And so like I threw out concurrency, I threw out inheritance, but I didn't throw it out in quite such an explicit way as I threw out concurrency. But I don't think it was a lack of understanding, although maybe it was a feeling that since Smalltalk didn't have encapsulation, they really weren't doing what I was interested in, and so I just didn't pay more attention to them.
Hi, I'm Steve Heller. You're a 6170 student in 1980, and then your graduate seminar in distributed objects in around 85. I have a question for one of your lecturers. Actually, now I'm at Sun Labs, and you mentioned that you don't like the use of syntactic abstraction, like the exclamation point for factorial.
Yeah.
And these days, there's a lot of work in domain-specific languages, which is essentially that in spades. So is that all wrong?
Well, back when I was back in the day, there was a lot of work on domain-specific languages. And I think that, if it's a big domain and you have a trained set of people who are all working in that domain, then having a specialized language for that domain is fine. What I don't think is good is anybody and his brother can decide to provide a little extra syntax, and then all of a sudden their programs are no longer in a standard dialect. And that, I think, is bad, because then you do lose readability.
But
I'm also not so convinced that people pay enough attention to readability. Even in the absence of syntax, it can be hard to read programs, especially with a lot of inheritance in them and so forth and so on.
But if the physicists need to have some specialized thing because they're experts in something, unless we want them to be designing the language, we need to give them a language they can extend.
Yeah, so I think, well, a language they can extend, or we could extend it for them. So and then there's a question of what's an extension. Is it syntactic or is it just more stuff?
Okay, thanks.
Yeah.
Hello, this is William Cook, and I want to say that I really appreciate your talk, and I'm going to be giving a talk later on that addresses some of these same issues, so I feel like I hope you can stay. We're involved in a conversation. I think that we're mostly consistent in our views, but I'm going to be giving a different take on things. I also want to say that I really like the style of research you do. I've done programming language research. I'm working on distributed systems now, so I feel like I'm following in your footsteps in a lot of ways. And so I appreciate that leadership. The last thing I want to say is that I think that I have to defend inheritance a little bit. So, in a way, I agree with you that subtyping and inheritance are different, and subtyping is perhaps more important. But I think inheritance is probably one of the most misunderstood things in object-oriented programming. And I guess I can claim some connection there because I have a PhD, and my topic is the semantics of inheritance. So I'd really like to actually tell you at some point what that is.
But probably not right now, right?
Not right now, because you may not have ever heard of it.
Okay.
Anyone else who wants to talk about it is one of my pet topics. So thank you very much.
You're welcome.
Hi, Carl Alphonse from University of Buffalo. I was wondering if you could tell us a little bit about how you became interested in computing to start with, and if you had anything to say about enrollments and in particular underrepresentation in the field.
Yeah, well, of course, when I was a student, there was sort of zero representation by women. And today, of course, we have a very low representation of underrepresented minorities. I got into programming by accident. I graduated with a degree in math. I didn't want to go to graduate school right away. I couldn't get an interesting job as a mathematician, so I got a job as a programmer. And so, and then I discovered I had a flair for it. And after a couple of years, I decided to go to graduate school, and this is really early. You know, there weren't that many places that had programs, and I ended up going to Stanford. So it was sort of accidental that I got into programming. Nowadays, I am actually Associate Provost for Faculty Equity at MIT, which means I'm looking out for especially women and underrepresented minority on the faculty. I think that, however, in computer science, although the representation of women is much better than the representation of underrepresented minorities, what we really have is a pipeline problem. And the problem goes back to high school and elementary school. At the university level, what we can do is we can watch out for our introductory courses to make sure that they aren't sort of male-dominated, so that young women who come in who maybe haven't been hacking for the last 10 years don't feel completely overwhelmed by the material, so you can work on that problem. But beyond that, we have a societal problem. And you know, we have a societal problem in general anyway, because in the United States, there's, you know, math and science are sort of looked down on by a large segment of the population. We even lose men, I think, you know, and we lose women. So there's a limit to what we can do at the universities. The other thing we can do at universities is we can try to foster promising students and look out for the young women and underrepresented minorities and try to bring them along in research so that they'll go on to graduate school and become, you know, have careers in computer science. But that's, I think, about what we can do.
Okay, thank you very much.
John Field from IBM. I'm curious if you think there could ever be too much encapsulation, particularly in languages with multiple abstraction mechanisms like inheritance, objects, interfaces, and so forth.
I don't know how to answer that question. You know, as I said, I've been sort of over there in the systems world. And, you know, the truth is, in the systems world, when we implement, we use C or C++, by and large. And the reason is because we're building platforms, and you know, performance really matters at the level of the platform. So I've had very little experience in programming in some of the, you know, the sort of modern languages, and so I don't have the kind of experience to answer your questions.
Thanks.
Hi, Pablo Figueroa, Universidad de los Andes. Sorry for another programming language question.
Yeah.
What do you think about aspect-oriented languages and aspects as a modular concept, a new modular concept?
The little I know about them concerns me. I know that Gary's been doing a lot of work on them, trying to sort of figure out what exactly is the semantics of what's going on. It's very important to have well-defined semantics and to be able to look at the code. So I'm back on Dykstra's argument. You know, code reading is important. When you read code, you have to have a pretty simple way to understand what you're looking at and how that relates to what's happening. And I do feel like there's a lot of stuff going on in programming languages that violates that principle, and that concerns me. But I can't tell you specific things about specific mechanisms because, as I said, I'm over there in the systems world and not paying a lot of attention.
Thank you.
Yeah.
Guy Steele, Sun Labs. I want to thank you, Barbara, for emphasizing the value of history. And that was a really great list of papers you put up, and I wish there were more awareness of those papers today. So I recommend those to everyone in the room if you haven't read them. My question is concerning the connection that you spoke of between CLU and Alphard and the creation of iterators for CLU. This problem of combining two abstract iterators was a difficult one. You chose to limit that in CLU.
Right.
And Alphard was saddled with much more difficult implementation.
Right.
This is still a problem that I wrestle with today. You've got two abstract iterators. What is the right way to combine them? In working on my own current research project, I have gone back and studied the papers about CLU and Alphard and stuff that's been done since then. I'm still not quite sure what the right answer is. Can you throw me a scrap? Do you have any further thoughts on this problem?
Well, in the end, I came down on the side of a sort of a simple, straightforward mechanism that could be implemented efficiently. You can always do the other. I mean, we know that you can implement generators using objects. And so maybe, so my take on it would be provide in a language the straightforward thing that solves most of the problem. This is always a problem in programming language design, right? I mean, there's the 90% solution and the 100% solution, and the 90% solution might be much better from the point of view of you capture it mostly, it's much simpler, the semantics is more straightforward, and then, you know, you sort of leave it up to the users to implement the structures. So you might turn that into here's a methodology for doing it as opposed to here's a programming language construct.
Okay, thank you. Maybe I will go for the 90% solution. If someone in the room can find the 100% solution for me, I'd be very grateful.
Of course.
Thank you.
Okay, Bard Bloom. I started in computer science down the hall from you at Tech Square. Now I'm at IBM Research. And I've got another little historical question. One of the things that I remember from CLU very distinctly in trying to get my head around was it had both mutable and immutable records and arrays.
Yes.
And I wanted to ask what the history of coming to that decision was.
That was sort of a uniformity argument. So we just sort of thought that if there was one, there should be the other. I mean, one thing that happened in the development of CLU was we became more and more interested in the difference between mutable and immutable types. And so we paid a lot of attention to that. But I think it was just, if you have mutable arrays, why not have sequences? If you have, you know, mutable, I don't know that we had immutable records. Yeah, I guess we did. We had structs, right. Yeah.
Okay, thank you.
Yeah.
Hello, my name is Jennifer Haddock-Schatz. I work at Daniel H. Wagner Associates in Virginia. First of all, thank you for being here.
You're welcome.
I have an education question. Back in the late 90s, when I was first learning about OO and polymorphism and inheritance, I remember the way it was taught, looking back on it, was very naive. I remember learning about creating a shape class and then creating a circle and a rectangle and a polygon class as subclasses. Right. It wasn't until several years later, you know, during my first internships and then later working in industry, that I think I really got the point that you were trying to make with the Liskov substitution principle. And now I don't know where I would be without it the past 5 years trying to maintain one software system. My question is, how do you think we can change the way we teach students in introductory courses, introduce them to OO principles so that they pick up the good habits early? Because what I fear is, I was lucky, the internships I walked into, I worked with a lot of good people with a lot of experience, and so I sort of got it eventually. I've seen too many people who still don't get it, and I think that's an education failure. And so I'm wondering what your thoughts are on how we can better get people to pick up those good habits from the start.
Yeah. Yeah, well, unfortunately, it's a hard question. So I did develop a course at MIT. It was our second programming course, and it had all this stuff in it. Especially in this later incarnation when I moved it to Java, you know, so I was teaching it in an object-oriented language, and so I did talk about the Liskov substitution principle and a whole bunch of other stuff about how to write specifications and how to reason about correctness. One thing that might be interesting to you is I had the students define all the rep invariance and abstraction functions, and I also had them implement them because they're very useful to have around when you're debugging. You know, so that was a course that focused on methodology, but those courses are not that common. I also don't think that should be a first course. I think you have to start with something much more gentle, and maybe object-oriented programming isn't even in it. You know, maybe you start by just focusing on sequential programming and how do you write simple algorithms and so forth. But you know, the truth is people have been wrestling with this for 40 years. And I do think, though, that it's really good to relate this more theoretical way of looking at things with the actual building of programs. And that's the way it sort of comes home. And I also think that, in fact, having the students implement the rep invariant and abstraction function, that was a really good way of getting them to appreciate their importance. So that kind of stuff you can do. And maybe you could do something like that for the Liskov substitution principle. It might be possible, so I haven't thought about that. So I'm saying it's probably not the first course, it's a later course, but it ought to be focused on sort of not what people call software engineering, where they're sort of interested in writing, doing things according to somebody's idea about how you do it, but more about how do you do modular program construction, how do you reason about the correctness of programs. That ought to be, together with actually writing some programs, that ought to be a fundamental part of our curriculum at the sophomore or junior level.
Hi, Shri Ram from Brown. I wanted to say thanks for the history lesson. I hope my students in the room paid as much attention to it as I did, because that's how wonderful it was. One of the strong positions you took in your talk was to make unequivocally clear you don't like this idea of syntactic extension or syntactic abstraction. So I thought I could push back against that just a little bit. You gave us one answer, which is don't do it. Another answer, which is, well, come to the language implementer and have them do it for you, which obviously is not a scalable solution. But there's a third answer out there, which is to say, and this will be shocking when you hear this word, modularity, right? Why is it that you assume that if I make a syntactic extension, it has to be global in scope? Why can't syntactic extensions be scoped just the same way other extensions are? Libraries are scoped, APIs are scoped. So if we scope our syntactic abstractions, then I can build one for myself, use it in my program, make clear where it's coming from, where it's being used, just like any other abstraction in my language.
Well, I mean, I can only sort of reiterate what I said, which is, if the symbol that you're using is very obvious and intuitive, then people who are reading your program may not have any trouble with it. But you really need to think about readers and readers next year. And you really want the way that the program looks to be sort of pretty self-evident. So this is really the reason why I'm not too enthusiastic about syntactic extensions, scoped or not.
Okay, thanks.
I'm Ralph Johnson from University of Illinois, and that was a great talk, and I'm going to be having my students in my object-oriented design class read your paper next semester, because I always have a little historical background part, and that is really a great. One objection I want to make was to your claim, or your statement, that in small talk there's no encapsulation. So that is true from a class point of view. There's no encapsulation of class definitions, but there's extremely strong encapsulation of objects. And so it sort of depends. I mean, it sort of shows that you're a type bigot. The statement, small talk has no encapsulation is true from a type point of view, but if you're an object bigot like me, then it's a completely false statement. So I just wanted to clarify that.
Well, actually, if you remember what I said was as far as users of the objects were concerned, there was no problem. I was much more worried about the code that inherited from the subclass.
Yeah, you made a statement. I just wanted to sort of qualify that statement. And there's an
said
interpretation in which it's true, there's an interpretation in which it's false.
I think I said actually small talk has encapsulation from the point of view of the users of the objects. So at any rate, it was Simula that did not have encapsulation, at least at the time that I did the work on Clue. But anyway,
Anyway, I wanted to thank you for a great talk.
Okay. Thanks.